So, as said in the video, there were some key discoveries that he basically put together for these objections that people had to the Copernican view. So let's go through that. Okay, so overcoming this first objection, and this really comes to the nature of motion. So Galileo did experiments that showed that objects in air would stay with Earth as it moved. Aristotle thought that all objects just naturally come to rest. But that's actually not true. Now, of course, if you roll a ball, right, down a flat area, it's eventually going to come to rest. But that's because there are frictional forces that are going to stop the ball, a little bit of air resistance as well. So, but if you could throw a ball, say, in space somewhere not near any planets, it would just keep going forever. So Galileo showed that objects will stay in motion unless a force acts to slow them down. And this actually is what Newton calls his first law of motion, but we're not quite there yet. Okay. So what that means is that that if there's no force just to sort of hold things back if the Earth's rotating or spinning around the sun, then these objects like air and birds and church steeples, etc., will just move along with the Earth. There's nothing to push them in another direction to make them fall off or whatever, right? Or topple over, right? And then the second objection, which was this idea of heavenly perfection, Tycho already had some observations of comets and supernova even that already challenged this idea that the heavens were perfect, because if there's some comet going around, that's certainly not part of this crystal spheres type perfection, or a supernova even. But using his telescope, Galileo could see that there are sunspots on the sun. Probably shouldn't have been looking at the sun. But he could see these imperfections, right? Things that didn't look like they were part of this perfect heavens. And he also saw mountains and valleys on the moon, proving it was not really a perfect sphere, but it's kind of a bumpy surface. Certainly, again, not part of a heavenly perfection. And then this last thing, parallax, Tycho thought he had measured stellar distances, so the lack of parallax seemed to rule out an orbiting Earth. But he hadn't actually measured their distances. Galileo showed that stars must be further than Tycho thought. In part, he used his telescope to see, the galaxy, the Milky Way, and see that it's countless individual stars. If stars were much further away than was thought, then the lack of this detectable parallax was no longer so troubling. So we haven't really discussed this yet, but you can do this experiment yourself. So if you can close one eye or the other, or maybe use your one hand to close one eye and the other, and put your finger at arm's length, you can see your finger sort of jump back and forth when you open one eye and then the other, right? So that's the different points of view. Your two eyes are different places on your head. And if you move your finger closer, the jump will be bigger. So parallax gets smaller the farther away the object is. And so if the stars are much farther away than was originally thought, then maybe parallax was too small to measure, which in fact was the case. So the parallax argument also went out the window. Okay, and just to mention about the telescope, they say, Galileo was using these telescopes. Well, the telescope was invented by Hans Lippershey, and really for military purposes, right? I mean, you can imagine that if you put these two lenses, we'll talk more about telescopes later, but if you took these two lenses, you passed light between these two lenses, that you could magnify a distant object. So you could see things that are really far away. Well, of course, the first thing that anyone thought about using that for was for military operations. So you could look and see a faraway army, see how many men they had, etc., right? So looking at faraway things for that purpose. But Galileo, of course, realized that telescopes could be used to image astronomical objects, and he built his own telescope in 1609, which he used for all his observations. Now, another thing that was sort of a nail on the coffin for the Ptolemaic view, the geocentric view, was the fact that Galileo used his telescope to look at Jupiter, and he saw these little moons, or little points of light. And in fact, if you come or go anywhere and look through a telescope at Jupiter, you will see these little points of light next to it. And those are the biggest of Jupiter's 69 moons. So Jupiter has 69 moons, but only 4 of them are really of any size, and those are the ones that Galileo was able to see, and they're called the Galilean moons for that reason. And from largest to smallest, there's Ganymede, Callisto, Io, and Europa. Very interesting worlds. We'll talk a little bit about those later. But anyway, he saw these moons and he could see that they're orbiting Jupiter because he would look night after night, and that's pictured here. Here are some of his drawings, and see that they would move into different position because they were actually orbiting Jupiter. Right? So it's a really cool observation to do yourself too. If you have a small telescope, it's all you really need. You can track these things. And so, that didn't really fit into the geocentric model, right? If Jupiter had moons orbiting it, then certainly Earth can't be the center because, right, Jupiter has its own moons that are orbiting it. So that didn't really fit. And of course it proves that not all objects orbit Earth. Okay, well, we talked about the phases of Venus, and then the careful observation of the phases of Venus really showed it had to be heliocentric, because if it was geocentric, the phases would be very different. So that was a very big deal. And you can kind of see up here that in a geocentric system, you really only expect to see these crescents and then, nothing, and then more crescents. And here in the heliocentric, you see lots of different phases, right? Quarters, gibbouses, crescents, fulls, and that's what was observed. So again, kind of no other way to see that unless Venus is going around the sun, and so is Earth. Well, of course, the Catholic Church did not like this. They had adopted the Ptolemaic view, and they ordered Galileo to recant his claim in about 1633. And his book that he had written that was mentioned in the video, the dialogues, were banned. So added to a list of banned books. And he wasn't even formally vindicated by the Catholic Church until 1992. So they took their time on that one. So again, this is his, he had written this book, Dialogue on the Two Chief World Systems, and he was brought before the Inquisition and was forced to recant, and he was sentenced to permanent house arrest, right? So he was a little bit confrontational with them. So and this is luckily he wasn't killed, which is certainly possible, or jailed, but he was put on house arrest. So let's do a couple of questions. Well, how initially did the inventors of the telescope plan to use it? Well, of course, makes sense, military use. And I think today this also happens that there are things that are that originally thought up and used for military purposes that end up being technology that we use all the time. A good example is GPS satellites, right? They were originally put up to, obviously for tracking things on the Earth, knowing where things are on the Earth, but for military purposes, and of course we use them all the time, every day. Not an unusual thing. All right. What's the largest moon of Jupiter? Well, Ganymede. Silly question, but nice to know if you at least know their names. You don't really have to know that it's the largest one, because you can look that up. All right. The discovery of the 4 Galilean moons of Jupiter supported what model of the universe? Well, of course, if Jupiter has moons orbiting it, then really not everything can orbit the Earth. So it's really the Copernican model of the universe that supported. Okay, the rough cratered surface of the moon and the presence of sunspots on the sun indicated that Aristotle's view of the perfection of the universe beyond Earth was an error. Well, that is true, right? Really can't have perfection if you've got sunspots and craters and valleys on the moon, etc. Again, another nail in the coffin for that view. Okay, so interestingly, being put on house arrest didn't really stop Galileo. So he decided to study the motion of falling objects, which he could obviously do from home. And he disproved the notion that Aristotle had put out and had held for a very long time, that all falling objects move with constant speed. Now you'd think that people would notice that that wasn't the case, but it really hadn't been formally put out there. He showed that they accelerate as they fall, increasing their speed. So if you look at this little experiment over here, right here at time 0, you drop the ball at, so if you look at the elapsed time, so 1 second, you've got 9.8 meters per second. That is the velocity. So 9.8 meters in every single second, right? And then after another second, you have 19.6 meters per second, and after another second, 29.4 meters per second. So it's getting faster and faster as it falls. Okay. And notice, right, that this here, after 1 second, is 9.8 meters per second. This is double this number, right? 9.8 times 2 is 19.6. So after 2 seconds, it's like double the velocity, and after 3, triple the velocity, etc. Triple the initial velocity of 1 second. Okay. All right, so let's study motion in much more detail. Because this really is starting to get into the real science of astronomy and physics. Galileo really made a huge contributions to that, as you can see. All right, so first we have to decide on how to talk about motion, how to describe motion. All right, there are very precise definitions that we use for describing motion in physics and astronomy. For instance, speed, that's the rate at which an object moves, and it has units of distance over time. For instance, miles per hour, meters per second, kilometers per hour, etc. Those are all, the miles and the kilometers and the meters are all units of distance, right? And then the time can be seconds or hours or whatever, right? And in this class and in most physics classes, for instance, they'll use meters per second as sort of the standard. But if you don't have a good intuition for how fast, say, 10 meters per second is, it's a good idea to, type that into Google and see what that is in units that you could understand better, like miles per hour. Okay, so, and then there's something called velocity. Now, you might think velocity and speed are the same, but they're really not, because velocity is what we call a vector, and we'll see those a little bit more later. And that is, it has actually 2 attributes. It has speed and direction. So you need both of those to specify the velocity. So if I say my velocity is 10 meters per second, I actually am not telling you all that I need to tell you so that you could know my velocity. I need to tell you also that it's due east, let's say, or 50 miles per hour north, right? I need to tell you a direction along with the speed. The speed is just the speed. So you could say, I'm going 50 miles an hour. You don't need to know the direction. But if you want to know my velocity, you got to know my direction as well. Okay, now acceleration is any change in velocity, not speed, but any change in velocity. And it has the units of meters per second, which is why there's a second squared here, okay? So for instance, here's a car that's accelerating, right? Its velocity is increasing, but it's going in a straight line, so its direction has not changed at all, right? So it accelerated from 30 kilometers an hour to 60 kilometers an hour, but it didn't change its direction. But its velocity is changing because its speed changed, right? Okay, now here is a car that's also accelerating, although you may not think of it that way. In the way that you probably think about acceleration. You don't think of this kind of thing where the speed doesn't change as acceleration. But it is, because the direction is changing. So if you change either the speed or the direction or both, you're changing the velocity. And if you change the velocity, you have acceleration. So this car is staying at 60 kilometers per hour during this whole curve, but its direction changed, right? First the direction is this way, and then the direction was this way, right? So different direction, so that is an acceleration. And then here we have a car that started out at 60 kilometers an hour and then ended up at 0 kilometers per hour. It's also accelerating, but we usually call that decelerating or negative acceleration, okay? Okay, so let's just talk about that a little bit more, and I'm going to use my blackboard just to show you how we represent things like velocities and accelerations. because we're going to need them when we start talking about forces. So in general, what we do is we represent the velocity as this thing called a vector. And I don't know why my pen's not working. Hold on. All right, so what we're talking about here is if we think about velocity, we represent it with something called a vector, which we represent graphically as a vector with a particular direction. So for instance, this would be to the right, right? Because the arrow's pointed to the right. So it's an arrow, that's pointing in a certain direction. The direction it's pointing is the direction of the velocity. So, and the length of the arrow we write as proportional to the speed. So we have length is proportional, that means proportional, that thing that looks like alpha, to speed. And the direction is given by the arrow. Right? Okay. So for instance, if let's say this is equal to, boy, I'm bad at drawing arrows, 100 meters per second, right? This length, and it's to the right, to the right. Then let's say this would be 50 meters per second. So notice it's half as long to the right. And maybe we'll draw one 50 meters per second to the left. So it's very convenient because it takes both of these things into account for this thing called velocity. There are other vectors. For instance, the acceleration is actually a vector, and we'll talk about that when we talk about forces. Forces are also vectors. They have how strong the force is and what direction the force is. So if you need to push, your cup across the table, right, you're going to exert a force on the cup. Let's say you need to push it to the right. You're going to push to the right with a certain amount of force. And if you push too hard, the cup's probably going to fall over, right? So the length of the arrow would be how hard you're pushing, and the direction of the arrow's pointing would be what direction the force is. So we'll talk about that more later. Okay, so falling objects have an acceleration, and this acceleration is of course due to gravity. So, and we saw that in the little experiments where we talked about that Galileo did, looking at finding that the velocity changed as the object fell farther and farther down. And here's another sort of depiction of that. At t equals 0, we don't have any velocity, and then he's going to drop the ball, right? So he drops the ball, and at 1 second, it's about 10 meters per second. It was 9.8 there, but we're just rounding up to 10 here. 2 seconds, at 2 seconds, it's 20 meters per second now. So it's getting faster and faster. So there's an acceleration due to gravity, or the acceleration of gravity. And all falling objects accelerate at the same rate on Earth. If you went to another planet or the moon, it would be different. But all falling objects accelerate at the same rate, not counting friction or air resistance. You got to ignore all that. Okay. On Earth, we call the acceleration due to gravity G, for gravity. Little g, as you see here. And it's approximately 10 meters per second per second. On the other slide that we saw, it was 9.8. Again, we just round up. Okay. And so this increases speed by 10 meters per second every second. So you can see that here. 0, then a second later is 10 meters, and then it increases by another 10 meters per second after 2 seconds. Okay. Now, the acceleration of gravity does not matter on the mass, does not depend, on the mass of the object falling. And Galileo showed that. It's the same for all falling objects, regardless of their mass. Now, you may not think that's true just from the way that that you've observed the world works. So, for instance, if you drop your keys or you drop a piece of paper, they're not going to hit the ground at the same time. But that's, and yes, the piece of paper does weigh a lot less than your keys probably, right? But it's because there's air resistance on the paper, and you can see that just probably from the way if you drop the paper, with the flat side up, you'll see it sort of waft down, right? So the classic example is a hammer and a feather, right? So if you drop a hammer and a feather on Earth, you're going to see the hammer fall quickly to the ground, right? the bang, and then that feather is going to sort of waft its way down, but that's because there's air. Right? Air is sort of buoying the feather up as it falls down. There's a lot of air resistance for that little feather. So let's look at this experiment, exact experiment, hammer feather on the moon where there is no air. Okay. Here we go.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
There it is. Yeah.
Mr. Galileo was correct in his findings.
There you have it, right? With no air resistance to slow that feather down, this very light object, the feather, and the very heavy object, the hammer, are going to hit the ground at the same time. And Galileo showed that. And a lot of people thought that wasn't true, right? Just because from everyday experience, we just don't experience it that way a lot of times. Okay, so now we have to start talking about acceleration and its relation to force. Well, anytime you have a net force, and I'm going to be clear about what that means in a second, you will have acceleration. So a net force causes acceleration, changes in velocity, right? That's what acceleration is. If you don't have a net force, you're not going to change your velocity. So let's take a look at a simulation for that. Oh, actually, it's down here. Here we go. All right, so this little simulation is kind of cute. It has different objects. So I'm going to start with a textbook. And it's supposed to be here on the floor. And then we have a guy here who's supposed to be pushing this. When I use my mouse, I can make him push the book this, let's say, this way. And now the book is on the ground. And you know, if you tried to push a book on the ground, like, say you had a book, nice heavy book on the carpet, you'd have to exert a bit of force to get it moving, right? Because there's a bunch of friction from between the carpet and the book. So let's give it a try. So I'm going to push, and notice the vectors, right? So look at the blue vector. That's my applied force. And then the other way is the frictional force, the red force. And the net is this little green arrow. And the friction force eventually slows it down, right? And makes it stop. If there was no friction, so let's try that. Oh, to get it back over here, I gotta push it. Okay, stop. How about if I just reset? Let's do that. Because it just left the building. There's gotta be a reset here somewhere. Okay, so I reset everything. So now let's turn friction off. Here we go. No friction. So imagine the book's now on ice, right? Okay, pushing. All right, now I'm letting go. Notice there's no net force, right? There's no little arrow up here. And that book is going to go forever. Okay, as long as the ice lasts, it's going to go forever. Because there's nothing to slow it down. There's nothing to decelerate it. There's no force to decelerate it. And there it goes. See, here's the count on how far it's going to go. We could let it run, and it would just be forever, right? Okay, so let's turn our friction back on. And we're going to look at something a little heavier, like the file cabinet. Now it's going to take a little more force to get it going. Now notice over here we have a little diagram, and this diagram was what's called a free body diagram, and that just means that you don't actually see the file cabinet here, but it's the forces on the file cabinet. And notice there's a force due to gravity pulling down, keeping it from floating away, and there's a force due to the floor pushing back up, and they're in balance, which means there's no net force in the vertical direction. Okay, and so that's why this thing isn't taking off this way or sinking into the ground. All right, well, we don't have to worry too much about normal forces in this class, but we're going to try to get this going again. We're going to apply a force and see the friction force. In fact, the friction force gets bigger the more you try to apply that force. And at some point, my applied force will be bigger than the friction force. Look at the diagram above, right? Can you see that my applied force is bigger? The arrow's longer. than the frictional force arrow, which means my net force is going to be the green arrow towards the house. Okay? Now when I let go of my applied force, look what's left. Just a frictional force. Okay? Right? Notice that these vertical forces do not matter whatsoever, right? It's only this force now, the frictional force, the net force, is causing it to accelerate to 0, which it just did. Okay. So the way that we think about adding these forces, so notice that if I go back this way, right, I have the applied force in one direction, the frictional force in another, and I get a net force. Whoops, hey, I didn't want to do that. Right, I have a net force up there in the green. Well, how do I get that? How big that is? Well, it's pretty simple. So I'm going to come back here. Let's get a new layer. Okay, let's kill that layer. All right, so it's pretty simple in the sense that, let's say we have an applied force this way, right? Here it is. It's nice and big. All right, and let's say we have a frictional force that goes in the opposite direction, right? It's pushing against your motion. And let's say it's only this big. Well, you can see that this force is bigger than this force and in opposite directions, right? So the way that you sort of figure out how big your net force is that you see whatever the bigger force is and subtract off this length, right? So if we think about it, this length is right here to here. So what's left is this, right? This much force, and in this direction. Right? So the net force, this will be the net. Why am I using that without my pen? Okay. This is the net force. Right? Because it's what's sort of left over after I subtract off this frictional force. So you basically take the arrow and, whoops, oh. Just figure out what's left after you subtract. That's if they're going in the opposite direction. Now, what if you had two forces going in the same direction? Well, you just add them. So I basically think about just putting this little one at the head of that one, and then the whole net force is this whole long thing. So in other words, this could be one force. Maybe I'm pushing and my friend's helping, right? And so we add those together and we get the net force. Okay, so that's how we think about forces. They're vectors, just like velocity is a vector and acceleration is a vector. They have the direction that you're pushing and how hard are you pushing. Okay, let's try a question. So for each of the following, let's think about, is there a net force? Remember, that's equivalent to asking, is the velocity changing? And you have to think about the velocity as being both speed and direction. Okay, so let's think. A car coming to a stop. Well, the car is starting out with some speed, a non-zero speed, right? And then it comes to a stop. So yes, there's got to be acceleration, in this case negative acceleration, which we also call deceleration. So yes, there has to be a net force. And in fact, the net force is provided by the brakes, right? When you are stepping on the car's brakes. Okay, so what about a bus speeding up? Well, this is similar, right? We have a change in velocity. It's going from, let's say, 20 miles an hour to 40 miles an hour. So the speed is changing. The speed part of the velocity is changing. So that's also a yes. Must be a net force. Okay, and that's provided by the engine in that case, right? Okay. An elevator moving up at a constant speed. Okay, well, let's see. Is there any change in velocity? Well, it's moving up. Didn't change the direction and start going down or sideways. Okay, so the direction part of velocity doesn't change. And it says constant speed, which means the speed isn't changing. It's not getting slower or faster, right? So it must have no net force. The net force must be 0, because if there was a net force, it would be either speeding up or slowing down or maybe changing direction, right? So it has to have net force 0 in this case. All right, how about a bicycle going around a curve? Well, this is the same situation as we saw the picture of the car going in a circle, staying at 60 kilometers per hour the whole time, going around a curve in that little drawing we had. So the direction part of the velocity is changing here. And if the direction part of the velocity is changing, then we have acceleration. And to have an acceleration, we have to have a net force. So this, yes, must have a net force. And we'll talk a lot about that later. A moon orbiting Jupiter. Well, let's see what's happening. I'll just tell you that let's say in this particular case that the speed is changing, right? It has to change because depending on the eccentricity of the orbit, it could change a lot, change a little through the orbit. So we know the speed's changing, and certainly the direction is changing, right? So because it has to go on one part of the orbit, right? It's say moving to the right a little bit, but then it has to keep going around Jupiter. So it's constantly changing its direction as it goes around Jupiter. So there must be a net force because both the direction and the speed is changing. Okay. All right. And so we just wrote down the answers to all those on that slide. All right, your turn. Please pause video and answer the question.